Hello there. Welcome back to Midnight Ocean. I'm Velen, your guide to traveling through the wonders of the ocean. Tonight, we're going to explore the underwater caves. If these cozy moments calm you, I invite you to subscribe, share a comment, or leave a like. Now, get comfortable, take a deep breath. Don't be afraid, you're safe here. Let's dive deep into the sea and let our imagination guide us to a peaceful and deep night. The Yucatan Peninsula has no visible rivers. All the rainwater that falls on it immediately disappears into the porous limestone bedrock and flows through an underground cave system stretching hundreds of kilometers. The Ox-Belha system on the Mexican Caribbean coast is the largest mapped underwater cave system on the planet, with 435.8 kilometers of explored passages, at least 160 connected cenotes, and most of its tunnels never traversed by a single human being. The second largest, the Sac-Acton system, spans more than 376 kilometers. The two systems sit just a few kilometers apart, and once connected by divers, they will form the largest known cave system on the planet, larger than any dry cave. Many of these caves have seen fewer visitors than the moon. To understand this place, you have to start with the ground, or rather, with what's underneath it. The Yucatan Peninsula is made up almost entirely of limestone, a porous sedimentary rock composed mainly of calcium carbonate. When rain falls, it doesn't find thick soil or a river to run through. Instead, it seeps directly through cracks in the rock, descending until it saturates an enormous underground aquifer. The result is a landscape with no rivers, no surface lakes, but filled with circular openings in the ground called cenotes, holes where the ceilings of ancient caves collapsed, revealing crystal-clear water dozens of meters below. Limestone and water are a patient and destructive combination. Rainwater absorbs carbon dioxide from the air and soil, becoming slightly acidic. That diluted solution, over millions of years, dissolves limestone from the inside out, carving passages, corridors, and chambers. This process has a name: karstification. The result in Yucatan is an underground network unlike any other. Hundreds of kilometers of interconnected flooded tunnels, forming what scientists call an Anchialan aquifer, a system closed at the surface but connected to the ocean through the Earth's depths. Cenotes are the entrances to this submerged world. Scattered by the thousands across the peninsula, estimates range between 7,000 and 10,000 throughout all of Yucatan. They work like natural skylights above corridors that stretch for kilometers. Some are open to the sky, circular and sun-drenched. Others are enclosed chambers inside caves, accessible only through water. Each one connects, to some extent, to the larger network. Diving into a cenote near the coast and following its tunnels will eventually lead you to the sea, a freshwater crossing that ends in salt, all without ever leaving the water. The Ox-Belha system, with its 435.8 mapped kilometers, represents only the extent that divers have been able to safely travel through and document. What lies beyond the explored ends remains unknown. Exploring these tunnels is not recreational diving. It is cave diving, a discipline that combines caving techniques with technical closed-circuit diving. Divers carry multiple gas cylinders, guidelines to keep from getting lost, and their own lighting, since no natural light reaches these tunnels. An equipment failure 300 meters from the entrance is not an inconvenience, it's a fatal emergency. The depth of the passages varies considerably. Sections near the coast tend to be shallow and horizontal, forming labyrinths running parallel to the shoreline. Passages further inland follow vertical fractures in the rock, going deeper and running perpendicular to the coast. This geometry reflects the region's geological history. Fractures created by stress in the rock, widened over millennia by the acidic water that flowed through them. The Ox-Belha system and Sac-Acton share this same architecture. like branches of the same underground tree that haven't yet been seen touching, but almost certainly connect. The Maya civilization inhabited this landscape for centuries and paid close attention to it. For the Maya, cenotes weren't just sources of drinking water in a riverless region. They were gateways to Xibalba, the underworld. Offerings, human bones, and artifacts recovered from cenotes confirm their ritual use. The most complete and genetically intact ancient skeleton found in the New World, a young teenage girl named Naya, approximately 12 to 13,000 years old, was recovered from a passage in the Sac-Acton system at 42 meters deep. She died in that cave when it was still dry, before the end of the last ice age. The archaeological dimension reveals another layer of this place. These caves function as time capsules. Submerged and cold, the underground water has preserved bones, tools, charcoal, and structures with extraordinary fidelity. Every exploratory dive faces the dilemma of moving forward without disturbing what lies on the bottom. Sediment stirred up by fins irreversibly destroys archaeological context. Because of this, many locations remain secret. The very cave that holds 12,000-year-old skeletons was vandalized after the discovery was made public, with bones stolen before they could be properly studied. Preserving this system is just as urgent as exploring it. The Yucatan Peninsula today is home to cities, resorts, farms, and highways built on limestone that filters directly into the aquifer. Agricultural pesticides, untreated sewage, and fuel residues dissolve through the rock and reach the caves without passing through any treatment whatsoever. Contamination studies have detected heavy metals and organic compounds in underground passages kilometers away from the pollution sources. The same system that provides drinking water to millions of people in the region also absorbs everything those people throw away. There's a disturbing symmetry in this geography. The surface of the Yucatan Peninsula looks solid: forest, road, hotel, farm. But underneath, just a few meters down, begins a vast, dark, flooded world that stretches for hundreds of kilometers in every direction. Every step taken on the surface is taken on a cave ceiling. Every raindrop that falls here eventually finds that labyrinth and travels through it to the sea. What's above and what's below share the same hydrological fate, separated only by the thickness of a rock that water, given enough time, never stops dissolving. Inside these flooded caves, divers come across intact stalagmites and stalactites, formations that only grow in air, never underwater. Their submerged presence is direct geological proof that these caves were once dry. During the last ice age, sea levels were approximately 100 meters lower than they are today. The limestone was exposed and the caves were dry. Filtered rainwater formed stalagmites and stalactites, millions of them, ranging in size from a pencil to a large tree. These formations stopped growing when sea levels rose. Diving through these caves, you can see exactly where the water level was 12,000 years ago. The formations above that line are larger and older. Those below are smaller or non-existent. The underwater caves of Yucatan are a visible geological calendar. Stalagmites grow up from the floor. Stalactites hang down from the ceiling. Both need air, specifically air with a carbon dioxide concentration different from that of the water seeping through the rock. The mechanism is straightforward. Slightly acidic water passes through limestone, dissolving calcium carbonate along the way. When that water reaches a cave with air, it releases some of its carbon dioxide into the local atmosphere. Without the gas to keep it dissolved, the calcium carbonate precipitates, solidifies, and deposits itself layer by layer. Repeated over millennia, this process builds structures that can reach meters in height or length. The growth rate of these formations is extraordinarily slow. Under ideal conditions, mineral-rich water, stable temperature, steady dripping, a stalagmite grows between 0.1 and 3 millimeters per year. A formation 1 meter tall may represent between 300 and 10,000 years of uninterrupted growth. When the process stops, because the water stopped dripping, because the chemical conditions changed, or because the cave flooded, the formation is frozen in time. Its internal layers preserve records of temperature, precipitation, and atmospheric composition from the era in which it grew, making it a precise climate archive. What divers find in the caves of Yucatan defies immediate expectation. Stalagmites rising from the floor of completely submerged passages, stalactites hanging from flooded ceilings, intact, with their tips still tapered, exactly as they were left when the water reached them. This confirms that these formations grew in dry air. Underwater, the calcium carbonate precipitation mechanism that creates them doesn't work the same way. The presence of these submerged structures is therefore direct physical evidence that sea levels were far lower at some point in the past. During the last glacial period, which peaked around 20,000 years ago and ended gradually around 11,500 years ago, enormous volumes of water were locked up in continental glaciers. With less water in the ocean, sea levels dropped globally. In Yucatan, the difference was roughly 100 to 120 meters below current levels. That retreat exposed the coastal limestone, allowing the caves, which until then sat below the marine water table, to dry out. For millennia, while ice covered the temperate regions of the planet, these limestone chambers quietly accumulated their formations in silence and darkness. With the gradual warming that ended the Ice Age, the glaciers melted. The ocean rose slowly, on a geological scale, but perceptible over centuries. When the water level reached the entrances to the caves, it began flooding them progressively. The formations that ended up submerged stopped growing at that very instant. Those that remained above the new water level kept going, adding newer layers on top of the old ones. This difference in size between formations above and below the flood line creates what geologists call a paleoclimatic marker, a visible boundary in the rock itself that records where the sea once stood. Dating these formations with precision is possible. The most widely used method is uranium-thorium dating. Uranium dissolved in the water is deposited alongside calcium carbonate as the formation grows, while thorium, which is insoluble, is not incorporated. Over time, the uranium decays radioactively into thorium at a known rate. By measuring the ratio between the two elements in a sample, scientists can pinpoint exactly when that specific layer was deposited. This method makes it possible to date formations with decade-level precision in samples tens of thousands of years old, a resolution that turns stalagmites into geological clocks. The flood line visible in the Yucatan caves sits at varying depths depending on distance from the sea. The closer to the coast, the shallower the transition. The farther into the interior of the peninsula, the deeper a diver has to go to find it. This reflects the geometry of the aquifer. Saltwater infiltrates more deeply inland, keeping the freshwater-saltwater interface at greater depths. But in both cases, the boundary between old and new formations marks the same event. The end of the last ice age, recorded not in a book or a laboratory, but on the walls and floors of tunnels that most humans will never see. There is one unsettling detail in this story. The formations that grew while the caves were dry are, for the most part, irreproducibly ancient. They will not grow again, at least not on any human timescale. A stalactite that took 8,000 years to grow 15 centimeters can be snapped off by a careless fin in a fraction of a second. The underwater environment adds another layer of difficulty. Diverse and confined spaces, loaded with cylinders, have very little room to maneuver. An inadvertent brush against the floor stirs up sediment accumulated over millennia, dropping visibility to zero and making the return to the surface dangerously harder. These submerged formations are, in essence, the solid memory of a different world. When the Earth was colder, the sea was lower, and these caves breathed. When the climate shifted, the sea rose and swallowed them. What remains are limestone witnesses to a climatic transition that reshaped coastlines, forests, and civilizations across the entire planet. In Yucatan, that transition isn't buried in layers of unreachable rock. It's suspended in the dark, just a few meters deep in tunnels you can actually swim through, within reach of anyone who knows how to get there and has the discipline not to touch. Inside the caves of Yucatan, there is a phenomenon that throws off even experienced divers. The halocline, the boundary between fresh water and salt water. Fresh water from rain floats on top of the denser salt water that seeps in from the sea through the porous limestone. Because of the density difference, the two layers don't mix completely, creating a strange visual anomaly. The color of the water looks different on each side. Buoyancy shifts too, so during cave diving training you have to learn to adjust for it. When you cross the halocline, your vision blurs, as if you've swum into a liquid cloud. Light bends between the two layers of different densities, creating the effect of a second surface suspended in the middle of the cave, a completely real illusion produced by physics, not optics. Halocline is a compound word from Greek, halos, salt, and klinion, to incline. In oceanography, it describes any zone where salinity changes sharply with depth. In Yucatan, the phenomenon occurs inside the caves themselves because two types of water share the same system without fully mixing. Fresh water, which comes from rain and seeps through the limestone from the surface, and salt water, which penetrates laterally from the sea through that same porous limestone. Since salt water is denser, salt adds mass without proportionally increasing volume. It sinks and stays in the lower layers, while fresh water floats on top of it. The depth at which this boundary occurs varies depending on distance from the sea. Close to the coast, the halocline can be as shallow as 10 or 15 meters down. In the interior of the peninsula, it can sit 50 or 100 meters below the water table. The reason is hydrostatic. The farther from the ocean, the thicker the freshwater layer needs to be to generate enough pressure to hold back the salt water. This pressure balance is dynamic. It shifts with rainfall, with the seasons, and with any disruption to the system, such as over-extraction of groundwater from wells. The visual effect the halocline produces comes from a fundamental property of light. It changes speed when it moves between media of different densities. That change in speed causes refraction, the bending of a light ray at the boundary between the two media. Each layer of water has its own refractive index, determined by its salt concentration. At the boundary between fresh and salt water, that index changes abruptly. Light rays arriving at an angle are bent, distorting images of whatever lies on the other side, like an invisible curved mirror suspended in the water. When the halocline is undisturbed, no currents, no disruption, the effect is even more striking. The boundary between the layers becomes visible as an undulating surface, with reflections and refractions that mimic exactly what the water's surface looks like when viewed from below. Divers describe the sensation of seeing a second mirror-like surface inside the cave, below the ceiling and above the floor, as if there were a liquid floor hanging in the middle of the passage. Wikipedia specifically describes this phenomenon in coastal limestone caves. The halocline can create the optical illusion of an air space inside completely submerged chambers. Buoyancy changes when you cross the halocline because buoyancy depends on the difference between the diver's density and the density of the surrounding fluid. Salt water is denser than fresh water, about 25 kilograms more per cubic meter, depending on salinity. A diver calibrated to float neutrally in fresh water will sink slightly when entering fresh water and rise when moving into salt water. That difference sounds minor on paper, but inside a narrow tunnel, a few meters from a stone ceiling, any unexpected shift in buoyancy has to be compensated for immediately using the buoyancy compensator or by adjusting breathing rhythm. There's no room for surprises. Cave diving training in Yucatan specifically includes drills for adjusting at the halocline. Divers learn to spot the layer visually before crossing it, to adjust the air in their buoyancy compensator as they pass through, and to maintain a horizontal position to minimize sediment movement on the floor. Crossing the halocline while stirring up the water temporarily mixes the two layers, producing intense visual turbulence that can drop visibility to virtually zero for several minutes. More than enough time for a disoriented diver to lose the guideline and get completely turned around. There are cenotes in Yucatan where the halocline isn't a simple boundary, but a layered structure. Cenote Angelita, near Tulum, is the most frequently cited example. Below the freshwater layer and above the saltwater, there is a layer of hydrogen sulfide gas, trapped between the two densities. This layer forms a thick yellowish haze that mimics the appearance of a cloud or fog floating inside a submerged cave. Submerged trees rise out of this sulfurous mist, creating images that look like photo manipulation but are completely real. 3 density boundaries, 3 distinct optical behaviors, in a water column less than 30 meters tall in total. The halocline also has a geological function that goes beyond the visual. At the boundary between fresh and salt water, the partial mixing creates a solution with a greater capacity to dissolve limestone than either layer has on its own. This phenomenon, known as mixing corrosion or anchialine speleogenesis, means the caves of Yucatan are carved most rapidly right where the two types of water meet. The halocline doesn't just mark the cave, it actively builds it, widening passages and opening chambers at the depth where the boundary between the two aquatic worlds remains suspended. Crossing the halocline is, in both a physical and symbolic sense, crossing a border between two worlds that coexist without dissolving into each other. Above, fresh water from recent rain, filtered through rock, carrying the memory of forest and sky. Below, salt water from the Caribbean, seeping through limestone over centuries, connected to the ocean through invisible fissures. Between them, a line that light cannot cross without bending, and that the human eye interprets as a surface, as a separation, as the end of one world and the beginning of another. It is a boundary with no substance, made only of difference, but just as real as any stone wall these caves of Yucatan have to offer. Anchialine caves, those connected to the sea through the subsurface, with no direct opening to the surface, are home to organisms that have existed longer than the dinosaurs. Remipedes are blind, unpigmented crustaceans that live exclusively in these caves. The remipedes found in underwater cave systems represent a crustacean lineage dating back 300 million years. They survived the planet's 5 mass extinctions, the breakup of the continents, the rise and fall of the dinosaurs, all of it from inside dark caves with no way out to the outside world. The halocline splits the community of organisms in two. Freshwater species live above it, marine species live below it, and the boundary itself acts as a barrier separating entire animal communities from one another. To understand what makes remipedes so extraordinary, you have to go all the way back to the Carboniferous, the geological period that ran from roughly 359 to 299 million years ago. During that time, dense forests covered continents still arranged in configurations we wouldn't recognize today, and winged insects were appearing for the first time. Fossils classified under the extinct order Enantiopoda, found in Carboniferous deposits in Texas, share enough morphological features with modern remipedes to suggest this lineage was already around by that period. The cave worked as a perfect refuge, stable, free of large predators, with a steady supply of organic matter carried in by water. Modern remipedes are unsettling-looking creatures. Their long, segmented bodies vaguely resemble an aquatic centipede. Each segment carries a pair of paddle-shaped appendages used for swimming. They measure between 1 and 4 centimeters in length, depending on the species. they are completely blind and unpigmented. In the absence of light, eyes and coloration are metabolically costly and useless, and selection weeds out what doesn't serve a purpose over generations. What remained were alternative senses, chemoreceptors capable of detecting organic molecules in the water at considerable distances, allowing them to locate prey in total darkness. Discovered only in 1979 and formally described in 1981, remipeds were initially classified as primitive crustaceans, a basal branch on the arthropod evolutionary tree. Subsequent molecular analyses, especially broad phylogenomic studies comparing thousands of genes simultaneously, arrived at a disturbing conclusion. Remipeds are the sister group to hexapods, the clade that includes all insects. This means the most ancient crustaceans inhabiting Caribbean underwater caves share a unique common ancestor with flies, beetles, and butterflies. The water-to-land transition that gave rise to insects, the most diverse animal group on the planet, may have started with something that looked a lot like a remipede. Nearly all 30 known species live exclusively below the halocline in the saltwater layer. That restriction makes sense. Remipeds have marine origins, and the Anchialan Aquifer kept them connected to the sea even as the surface of the Yucatan Peninsula became increasingly isolated hydrologically. The underground saltwater acts as an invisible corridor linking populations in caves separated by hundreds of kilometers on the surface. That same corridor explains why remipeds also turn up in the Bahamas Canary Islands and a cave in Western Australia, a disjunct distribution that only makes sense if you picture ancient oceans once connecting those dots. The halocline doesn't just separate remipeds from the freshwater organisms above, it structures an entire ecologically layered community. Above the boundary, freshwater crustaceans like blind shrimp of the genus Crioceria occupy the upper passages. In the mixing zone between the two water types, species tolerant of salinity variation find a specific niche. Below, in the saltwater layer, remipeds share space with mysid shrimp, amphipods, and other invertebrates of marine origin. It's an ecological stratification comparable to the vertical zonation found in oceans, but compressed into spaces a diver passes through in seconds. The remipede venom system is another surprise. Long considered passive filter feeders or detritivores, recent research has revealed that they possess maxillipeds, appendages near the mouth, modified into structures capable of injecting paralyzing venom. When capturing prey like a small shrimp, the remipede pierces the exoskeleton and injects enzymes that liquefy the internal tissues. The contents are then absorbed. This sophisticated predatory behavior, combined with a refined chemoreceptor sensory system, suggests that cave life didn't simplify these organisms. It simply redirected their complexity toward what was useful in the dark. The fossil record for remipeds is sparse for a straightforward reason. Caves rarely preserve fossils. Sediments in cave environments are unstable, and the water circulating through the tunnels continuously dissolves and redistributes material. The two known fossils from the order Enantiopoda represent the only solid evidence of this lineage's antiquity. What existed in the 300 million years between those fossils and the living remipeds of today is, for the most part, invisible to the geological record. That invisibility is not absence. It's the consequence of inhabiting an environment that erases its own inhabitants over time. Preserving remipeds means preserving the caves themselves. Any contamination of the aquifer, pesticides, fertilizer nitrates, domestic wastewater, seeps directly into the environment where they live. Groundwater in Yucatan doesn't go through biological filtration before reaching the tunnels. The limestone filters out particles, but not dissolved chemical compounds. Remipede populations are small, localized, and have no ability to migrate quickly to unaffected systems. A single localized contamination event can wipe out an entire population of a species that has existed uninterrupted for 300 million years, ended not by a mass extinction, but by an illegal sewage dump. Spotting a remipede inside a cenote is rare even for experienced divers. They live deep in the system, below the halocline, in passages that require technical diving to reach. When they do appear, they are nearly transparent, the segmented body and paddle appendages visible through unpigmented skin, the internal organs legible like a living anatomical diagram. Creatures that existed before the dinosaurs, that survived as continents split apart and oceans changed shape, now swim through the darkness of limestone tunnels in Mexico, untouched by the history that unfolded above them, unrecognizable to the world that exists on the outside. The fish that inhabit these caves in permanent darkness went through a very specific transformation. Their eyes regressed until they disappeared entirely. Stygobitic adaptations include elongation of appendages, reduced metabolism, specialized sensory systems, loss of eyes, and depigmentation. The loss of eyes is offset by the enhancement of mechanosensory organs like the lateral line system of neuromasts, which detects pressure variations and water movement. The Mexican cave fish, Astyanax mexicanus, has genetically identical populations living in rivers and in caves. Within just a few generations inside caves, the eyes regress and the lateral line expands. The same animal, under different conditions, produces two completely distinct morphs. Offspring from crosses between surface and cave morphs are born with partially developed eyes, a direct window into the process as it's happening. Astyanax mexicanus is a small fish, rarely exceeding 10 centimeters, belonging to the characid family, the same one as piranhas and aquarium tetras. On the surface, in the springs and rivers of the Tamaulipas and San Luis Potosí region of Mexico, normal Astyanax populations have functional eyes, full pigmentation, and diurnal behavior. In a significant number of geographically separate caves, there are populations with no eyes, no color, altered behavior, and expanded sensory anatomy. Both are classified as the same species because crosses between them produce fertile offspring, the fundamental biological criterion for recognizing a single species. What happens to the eyes inside the cave is not simply atrophy from disuse. The process is genetically active. Genes controlling eye development continue to be transcribed in cave populations, but are suppressed by other genetic pathways that simultaneously expand alternative structures. Research shows that supernumerary neuromasts, the extralateral line organs, partially develop in the orbital space where the eyes would normally grow. There is a direct trade-off. The same anatomical space and some of the same developmental resources are reallocated from a useless organ to an essential one. It is not passive degeneration, but active reorganization. The lateral line is a sensory system that fish have and humans have no direct equivalent of. It consists of a series of organs called neuromasts distributed along the body, each containing mechanosensory hair cells, similar to those in the human inner ear, but oriented toward detecting movements and pressure changes in the surrounding water. When an object moves in the water near the fish, it displaces water molecules in a pattern that the neuromasts register with millimeter precision. For a blind fish in a dark cave, this ability is equivalent to seeing the hydrodynamic environment around it, a continuous map of disturbances, currents, and obstacles translated into nerve impulses. In cave populations of Astyanax, the neuromasts are larger, more numerous, and more sensitive than those of surface fish. Experiments have measured the difference. Neuromasts in cave fish have cupullae, the gelatinous structures that cover the hair cells and amplify water movements, that are significantly larger, resulting in sensitivity to water flow roughly twice that of sighted populations. This increase is not accidental compensation. Genetic mapping studies show that the genetic loci controlling neuromass size and eye regression are clustered together in the genome, suggesting that selection operates on both simultaneously, not separately. The metabolism of cave fish also differs. In environments where food is scarce and unpredictable, reduced metabolism is an advantage. Spending less energy at rest means surviving longer between meals. Cave populations of Astyanax consume oxygen at lower rates than surface populations under resting conditions. They also store more body fat as an energy reserve. Together, these traits allow the fish to tolerate periods of nutritional scarcity that would be lethal for their river-dwelling relatives, where food is more abundant but less temporally concentrated. Behavior changes along with anatomy. Surface fish have a pronounced circadian rhythm. They are more active during the day, less so at night, synchronized by light. In caves where light does not exist, that cycle disappears. Cave fish are active at irregular intervals, responding to food availability rather than the solar cycle. They also lose schooling behavior, an anti-predator response that is unnecessary in an environment with no visual predators. Costly behaviors that don't contribute to survival in the new context disappear by the same logic that drove the eyes to regress. Crossing between populations provides the most direct evidence of the process underway. When a surface fish with normal eyes mates with an eyeless cave fish, the first-generation offspring are born with reduced eyes, intermediate between both parental morphs. Crosses between those offspring produce in the second generation a range of variation. Some with larger eyes, some with smaller eyes, some with no eyes at all. That pattern of genetic segregation indicates that multiple genes control eye size, and that the allelic versions present in cave populations differ from those in surface populations. The segregation makes visible the underlying genetics of a process that normally unfolds over thousands of invisible generations. Different Astyanax cave populations live in separate caves, geographically isolated, with no contact between them. Each colonized its cave independently from distinct surface populations. And yet all of them converge on the same adaptations: no eyes, no color, expanded lateral line, reduced metabolism. This independent convergence across multiple separate lineages toward the same set of traits is powerful evidence that these adaptations are specifically favored by the cave environment and are not the result of genetic accident. The environment selects, the solutions are predictable. Astyanax mexicanus has become one of the most studied models in evolutionary biology precisely because it allows researchers to compare, in the same lab, the ancestral and the derived form. The river fish and the cave fish cross them, sequence their genomes, and map exactly which genetic differences correspond to which anatomical differences. In the caves of Yucatan, this process is not finished. It is happening right now, in living populations, in real geological time. Every generation born in permanent darkness is a generation potentially further from the one that lived in the light. The cave is not just a habitat. It is a laboratory without walls, running experiments that have been going on longer than any human science. In 2007, divers exploring a section of the Sac-Acton system descended a 55-meter vertical pit and found at the bottom a chamber containing bones of extinct megafauna, giant ground sloths, gomphotheres, short-faced bears, and among them, the skeleton of a young human girl. With sea levels during the last ice age up to 100 meters lower than they are today, these animals had to travel through dark, dry cave passages to reach fresh water, sometimes surprisingly far from any entrance. Trapped in sinkholes or lost inside labyrinthine passages, these animals died, and their remains were fossilized and preserved by the rising water levels. The teenager, named Naya by researchers, was dated to approximately 12,000 years old, one of the oldest human skeletons in the Americas. The chamber where she was found is among the few places on Earth where 12,000-year-old organic matter is preserved intact. 3 divers, Alberto Nava, Alejandro Alvarez, and Franco Adelini, were exploring an unmapped section of Sac-Acton when they descended a vertical shaft. At the bottom, at 42 meters deep, a collapsed chamber opened up. The floor was covered in bones. Skulls and ribs of extinct animals rested among blocks of rock that had fallen from the ceiling. And in the middle of that ossuary was a human skull, turned upside down on a rocky ledge, surrounded by other bone fragments. The divers photographed everything without touching anything and surfaced to report the find. The chamber was named Hoyo Negro, black hole, for its absolute darkness and immense dimensions. Naya, a name given by the team in reference to water nymphs from Greek mythology, was a young woman between 15 and 16 years old, approximately 5 feet tall, with a slender build. Her skull displayed classic Paleo-American morphology: wide and low forehead, narrow face, widely spaced eye sockets, slight prognathism. This morphology is visibly different from that of modern Native American populations, a contrast that had puzzled researchers since the first analyses of ancient human remains on the continent. The question was whether the first humans in the Americas were biologically distinct from those who came later, or whether the morphological difference simply reflected natural variation within the same lineage. Dating was carried out using multiple independent methods. Radiocarbon dating of dental enamel yielded ages between 13,000 and 12,000 years before present. Uranium-thorium dating of calcite crystals that grew over the bones, deposited after the chamber was flooded, confirmed the same age ranges. The consistency between distinct techniques ruled out contamination or systematic error. Naya died between 12 and 13,000 years ago, when the cave was still dry, most likely by falling into the vertical pit in the dark, an accidental death similar to what must have happened to the animals whose bones shared the chamber with her. The biggest scientific surprise was not the age, but the DNA. Extracted from a molar tooth and sequenced using paleogenomics techniques, Naya's genetic material confirmed Asian origin via Beringia, the land bridge that connected Asia and the Americas when sea levels were low during the Ice Age. Her mitochondrial lineage belongs to haplogroup D1, present in modern Native American populations. That result settled a long-running debate. The morphological difference between Paleo-American skulls and modern Native American skulls does not reflect separate origins. Both share the same Asian ancestor. The shift in morphology over 12,000 years reflects genetic drift and environmental pressures, not separate migrations. The animals found alongside Naya make up a catalog of the region's Pleistocene megafauna. Remains of at least 26 large mammals were identified in the chamber, including Smilodon fetalis, the saber-toothed cat, gomphotheres of the genus Cuvironeus, extinct relatives of elephants, giant tapirs, mountain lions, jaguars, coyotes, coatis, and bats. Most of them likely fell into the pit in the dark, unable to escape the dead-end vertical shaft. The low oxygen levels in the groundwater, anoxic conditions that slow bacterial decomposition, preserved these bones for millennia in remarkable condition. The exceptional preservation at Hoyo Negro results from a rare combination of physical and chemical factors. Cold water slows the chemical reactions that break down organic matter. The low oxygen concentration prevents the metabolism of aerobic bacteria responsible for most decomposition in normal environments. The absence of disturbance, no scavenger can reach the bottom of the pit, kept the bones exactly where they fell. And the surrounding limestone, slowly dissolving in the water, deposits thin calcite crusts over bone surfaces, creating a mineral shield that still protects the genetic material preserved inside. Archaeological recovery of the site poses unique challenges. Working at 42 meters deep, inside an underwater chamber with no natural light, with technical dive equipment that limits bottom time, requires every operation to be planned with pinpoint precision. Sediment stirred up by fins can irreversibly destroy stratigraphic context. Underwater photogrammetry, a technique that generates three-dimensional models from overlapping photographs, was used to digitally map the site before any physical removal. Most of the bones remain where they were found, preserved by the same environment that protected them for 12,000 years better than any museum could. The chamber was vandalized. After the discovery was made public, unauthorized divers entered the site and handled bones. Some were displaced, others disappeared. The archaeological context of parts of the site was irreversibly compromised. That violation prompted a change in the project's disclosure policy. The precise locations of sensitive sites within the system are now kept confidential, shared only with authorized divers and researchers affiliated with Mexico's National Institute of Anthropology and History. Preserving what remains depends on keeping the site invisible to those who have no business being there. Hoyo Negro is not just an archaeological site. It is a chamber where time stood still. While the world above underwent radical transformation over 12 millennia, civilizations rising and falling, species going extinct, landscapes being reshaped, the interior of that vertical pit remained unchanged, its bones resting exactly where they fell. The cold, dark, oxygen-poor water acted like a sealed jar, preserving the past with a faithfulness the surface cannot offer. Below the cenotes, below the halocline, below the stalactites that grew when these chambers still had air, Yucatan holds an archive that begins where human memory ends. Between approximately 11,400 and 10,700 years ago, indigenous peoples mined ochre, a red iron oxide pigment, in the caves of Yucatan. After the mining ended, the caves flooded with the close of the Ice Age and the rise of sea levels, preserving the miners' camps, including the charred remains of their fires, allowing archaeologists to see exactly how the mineral was extracted. The still water of the caves preserved everything: campfires, tools, meal bones, traces of movement. In an environment with no current, not enough oxygen for decomposition, and no access for animals or fungi, time stopped. The site was described by researchers as an underwater time capsule, a work camp frozen at the exact moment the water rose and sealed the entrance. Ochre is one of the oldest substances intentionally processed by humans. Technically, it refers to any iron-rich rock that, when ground down, produces a usable pigment. In its red form, hematite, or heated hydrated iron oxide, it produces an intense color that doesn't fade easily. Ochre residue has been found at archaeological sites on every inhabited continent, associated with rock art, funerary rituals, hide processing, and possibly medical applications as an antiseptic or sunscreen. The fact that people in the Americas 12,000 years ago ventured, figuratively speaking, since the caves were still dry then, into extensive tunnel systems in complete darkness to extract this specific material reveals just how much ochre mattered. The discovery took place in 2017 when two divers from the Centro de Investigación del Sistema Acuífero de Quintana Roo, CINDAQ, squeezed through a passage only 70 centimeters wide after swimming nearly a kilometer inside a submerged cave system near Acumal. On the other side of that narrow passage was a chamber preserved in extraordinary detail. Piles of broken stalactite and stalagmite fragments, campfires with charcoal still intact, stone cairns stacked along the path, and a floor stained red. Those divers were the first human beings to visit that place in approximately 10,000 years. The fires inside the caves were necessary for a practical reason, and not for warmth. The caves of Yucatan maintain a constant temperature of around 24 degrees Celsius year-round. The darkness in the depths of these systems is absolute. There is no light whatsoever beyond what the miner carried in. Fires fueled with wood collected on the surface provided the only available light to work by. Researchers found charcoal from those fires up to 650 meters from cave entrances, evidence that the miners penetrated deep into the system and worked for extended periods by the light of flickering flames against rock walls. The ochre from the La Mina cave was no ordinary material. Lab analyses revealed a purity of 60 to 80% iron oxide by mass, an extremely high concentration compared to the reddish soil on the surface of that same region, which reached only 8%. The particles of cave ochre were ultrafine, smaller than 1 micrometer, practically ready for direct use as paint without any additional grinding. Whoever was extracting this material knew how to tell quality apart. They weren't collecting just any reddish rock, but specifically seeking out the highest purity deposits, identifiable by the intensity of the color and the texture of the exposed rock surface. The tools found at the site were improvised from whatever the environment offered. Broken pieces of stalactites and stalagmites served as hammers to fracture the surrounding rock and expose the ochre deposits. Organized piles of discarded fragments, the mining waste, were found systematically throughout the explored corridors. 155 cairn structures, intentional stone stacks, were documented, functioning as navigation markers in the lightless tunnels. A signaling system built to be followed in total darkness, with only the glow of a flame to illuminate the next stone marker along the way. The decision to mine in such a hostile environment required a powerful justification. Entering a pitch-dark tunnel system with no artificial lighting technology, squeezing through narrow passages, hauling heavy material back through hundreds of meters of winding path. All of that implies that ochre was worth the effort. In the prehistory of the Americas, ochre has been found associated with burials, painted onto bodies, mixed with animal fat as a leather preservative, and used in art. Any one of those functions could justify the undertaking, possibly all of them at once. A material with both practical and ritual uses tends to be treated as a strategic resource, not just a utility. At least 3 separate cave systems, all near Akumal, show evidence of the same pattern of mining activity. La Mina, Monkey Dust, and Sagittario all feature stone cairns, campfires with dated charcoal, improvised tools, and mining waste deposits that follow a consistent organization. This indicates that the practice was not accidental or isolated. It was an organized activity, repeated by different groups or by the same group on successive visits. The sites were used between approximately 12,000 and 10,000 years ago, according to radiocarbon dating of campfire charcoal. What ended the mining was not a human decision. It was the water. As sea levels gradually rose with the thawing of the glaciers, salt water pushed through the porous limestone, raising the water table inside the caves. First, the deepest chambers flooded, then the intermediate passages. Finally, the entrances were swallowed. This process unfolded over centuries, not days. Miners who periodically returned to the site must have noticed the water advancing progressively, eventually cutting off access to the lower chambers. By around 10,000 years ago, the sites were unreachable. The camp was left exactly as it was, because there was no way to carry back what had been left behind. On the surface, nothing from that period survived. The heat, humidity, and acidity of Yucatan's tropical soils destroy organic matter quickly. 12,000-year-old bones on the surface would have dissolved centuries ago. Wooden tools, basketry, leather gone. What remained in the underwater caves exists precisely because it was underwater. The stillness of cave water, low in oxygen and stable in temperature, turned these sites into the most complete records of the peninsula's earliest populations. The oldest civilization of Yucatan is not visible above ground. It is suspended in the dark, just a few meters deep, preserved by the same process that buried it. In the El Zapote cave, near Puerto Morelos in Yucatan, divers discovered bell-shaped structures up to 4 meters long hanging from the cave ceiling. Unlike normal stalactites, they did not grow in air, they grew underwater. Uranium-thorium dating of the calcium carbonate confirmed that these formations must have genuinely grown while submerged, proving that the Hell's Bells formed in ancient times. Even then, the deeper regions of the cave had already been submerged for thousands of years. They grow in a lightless environment, near the base of a freshwater unit immediately above a toxic, oxygen-free, sulfide-rich saltwater zone. Bacteria at the boundary between the two water layers produce the chemical conditions that precipitate calcite, a form of biological mining that creates structures that challenge everything known about how stalactites form. To understand why the Hell's Bells are extraordinary, you first need to understand why normal stalactites cannot exist underwater. The conventional formation mechanism depends fundamentally on air. Water saturated with calcium carbonate drips from the ceiling of a dry cave, makes contact with the cave's atmosphere, releases carbon dioxide into the air, and the carbonate that loses its gaseous support precipitates and solidifies. No air, no gas release, no precipitation. That is the physics governing stalactites everywhere on the planet, except, apparently, in El Zapote, where the underwater environment produced structures with similar morphology through a completely different mechanism. El Zapote is a cylindrical cenote with vertical walls that drop more than 30 meters down to a submerged chamber. The water column inside the cenote is stratified. At the top, oxygenated, clear, cold freshwater. Below a certain depth, the halocline marks the transition to salt water. In that transition layer, oxygen disappears, the zone is anoxic, and sulfide concentration rises sharply. Hydrogen sulfide produced by the decomposition of organic matter at the bottom accumulates in this intermediate layer, making it toxic to most organisms. It is precisely at this boundary that the Hell's Bells form. The Hell's Bells hang from the ceiling and walls, expanding conically downward in the shape of a bell or inverted mushroom. Hence the name chosen by local divers, who associated their eerie appearance with the conditions of the surrounding environment. The largest structures reach 2 meters in length. At El Zapote, formations up to 4 meters have been documented. Their surface features concentric bulges and constrictions, horizontal rings that alternate between expanding and contracting along the length of the formation. This ring texture suggests that growth occurs in pulses, possibly responding to seasonal variations in the conditions of the transition layer where they develop. The formation mechanism involves bacteria. At the boundary between the oxygenated freshwater above and the anoxic, sulfide-rich zone below lies a layer called the redoxglen, a 1 to 2 meter band where chemical conditions shift abruptly. A chemolithoautotrophic microbial community lives in this zone, organisms that extract energy not from sunlight, but from chemical reactions between sulfur and nitrogen compounds. By metabolizing sulfides and nitrates, these bacteria consume protons from the solution, raising the local pH, making the water more alkaline in that specific band, and calcite precipitates more readily at higher pH. The bacteria's own metabolic activity creates the chemical conditions that deposit the mineral making up the formations. The redoxglen is not in a fixed position. Hurricanes, heavy rainfall, and seasonal fluctuations in the water table cause the halocline to rise and fall. When the position of the boundary shifts vertically, the precipitation zone shifts with it. This explains both the concentric rings on the surface of the Hell's Bells. Each ring marks a different redoxglen position during a distinct period, and the fact that the formations span a 10-meter depth range within the cenote, rather than being concentrated at a single level. The bell grows downward while the ceiling stays fixed. The base follows the variation of the chemical boundary that provides it with the conditions to grow. The biology of the site goes beyond the calcite-forming bacteria. El Zapote is also home to algae and other microorganisms adapted to the extreme chemical interface of the redoxglen. Studies have identified microbial communities that in a lab setting would be classified as extremophiles, organisms capable of surviving conditions that would be lethal to most life forms. Ironically, the same environment that would kill any large animal within minutes sustains complex microbial communities that inadvertently build the largest documented submerged limestone formations on the planet. Submerged calcite formations are known in other locations. Needle-like crystals and phreatic speleothem deposits have been described in flooded caves in various countries. However, none reach the dimensions of the Hell's Bells, and none exhibit the same bell morphology with concentric rings. The specificity of the phenomenon to El Zapote and a handful of other cenotes in the northeastern Yucatan region suggests that the exact combination of conditions required, cenote geometry, halocline depth, water chemistry, specific microbial activity, and local hydrological patterns, rarely comes together all at once. These are geographically restricted, biologically mediated, and geometrically unique formations. Diving down to the Hell's Bells zone requires skill and careful planning. The formations sit close to the halocline, which means crossing it to reach them already involves a sudden buoyancy adjustment. The anoxic layer below must be avoided. The concentration of hydrogen sulfide is incompatible with conventional dive equipment and potentially fatal if inhaled. The diver must stay in the freshwater layer, as close as possible to the upper edge of the redoxglen, to observe the formations without descending into the toxic zone. It is a millimeter precision dive in an environment that does not forgive errors in vertical navigation. The Hell's Bells cap one of the strangest stories that underground Yucatan has to offer. The very same process that normally destroys organic matter, bacterial oxidation, consumption of reduced compounds, chemical transformation of the environment. Here, through the peculiarities of a specific chemical boundary in a cylindrical cenote in northeastern Mexico, produces solid limestone structures that last for millennia. Bacteria living on poisonous sulfides produce, without intention or awareness, the largest known submerged stalactites on the planet. Accidental biological mining, on a geological timescale, in an environment that should inhibit any mineral precipitation at all. The caves of Yucatan keep contradicting what seemed settled. 70 kilometers off the coast of Belize, in the middle of the Caribbean Sea, there is a perfectly round circle of dark water. The Great Blue Hole, 300 meters wide and 125 meters deep. It is a collapsed cave system that formed during the last ice age, when sea levels were lower. Stalactites at 40 meters deep confirm it was once an air-filled cave. When sea levels rose, the cave flooded and the ceiling collapsed, punching a perfect hole in the surrounding reef. Jacques Cousteau visited the site in 1971 and declared it one of the best dive sites in the world. Not for its marine life, which is sparse, but for the submerged stalactites at 40 meters deep, each one a geological record of the world before the end of the last ice age. The Great Blue Hole sits in the Caribbean Sea, not the Atlantic, though the two are connected, and the distinction is easy to miss on small-scale maps. Specifically, it is located at the center of Lighthouse Reef Atoll, a circular coral structure rising from the shallow Caribbean seafloor. Seen from above, from a plane or a satellite, the contrast is immediate. A circle of deep, almost black blue, perfectly round, in the middle of translucent turquoise water no deeper than 10 meters. That color difference is the depth difference made visible. Where light reaches the white sand bottom, the sea looks blue-green. Where the hole begins and the floor drops away to 120 meters, the water absorbs the light and gives back only darkness. The circular geometry of the hole is not an aesthetic coincidence. It is a direct consequence of the way limestone caves collapse. When the ceiling of an underground chamber gives way, the collapse propagates inward in all directions from the initial failure point, tending to produce a circular or elliptical opening. The blue hole went through this process in multiple stages over more than 150,000 years. Analyses of stalactites recovered from its walls reveal formation events in 4 distinct periods: 153,000, 66,000, 60,000, and 15,000 years ago, corresponding to different phases of the Quaternary glaciations. Each of those formation periods corresponds to a time when sea levels were low enough for the limestone chamber to be exposed to air. During those windows, stalactites grew from the ceiling and stalagmites from the floor, layer by layer, in darkness and silence. When the climate warmed and the ice melted, the ocean rose and flooded the chambers again. The formations stopped growing, covered by salt water. The next glaciation lowered the sea again, exposing the same space, and the process restarted on top of the older layers. What divers find at 40 meters deep are the accumulated results of that repeated cycle. Formations of different ages, layered on top of each other like chapters of a book that took hundreds of thousands of years to write. Some stalactites recovered from the blue hole are tilted 5 degrees off vertical, and all of them tilt in the same direction. Stalactites always grow perfectly vertical, following gravity. A uniform, consistent tilt across all formations in the same chamber indicates that it was not the stalactite that grew crooked, it was the rock beneath it that tilted afterward. This reveals that the limestone platform on which the blue hole sits underwent tectonic movement, a slow rotation of the geological substrate, at some point after the stalactites formed. The formations themselves function as paleogeological compasses, recording not just climate, but the movements of the ground beneath them. Jacques Cousteau arrived at the site in 1971 aboard the Calypso, his research vessel. The expedition confirmed the karst origin of the hole and mapped its depths. The initial measurement of 125 meters remains the most cited. Cousteau declared the Blue Hole one of the 5 best dive sites in the world, not because of an abundance of life, which is indeed limited inside the hole, where the lack of oxygen circulation makes the environment anoxic below 90 meters. The draw is the descent itself, vertical limestone walls dropping away into growing darkness, with stalactites emerging from the rock like ribs of a structure that was once dry and now breathes salt water. The interior of the Blue Hole is not simply a flooded cave. It is a stratified environment with distinct characteristics at each depth range. In the first 5 meters, the coral reef surrounding the rim of the hole is teeming with life. From the point where the shallow atoll floor disappears and the vertical wall begins, life thins out progressively. At 40 meters, stalactites appear on the walls, suspended in a half-lit environment where pressure is already 4 times that of the surface. Below 90 meters, a layer of hydrogen sulfide forms a visible haze, similar to what appears in the Yucatan cenotes, below which oxygen disappears entirely. In December 2018, 2 submarines descended to the bottom of the Blue Hole to create the first complete 3-dimensional map of its interior using sonar. The expedition, funded by Richard Branson and including Fabien Cousteau, Jacques' grandson, documented the sulfide layer, mapped the wall formations, and also found the bodies of 2 divers who had previously gone missing at the site. The sonar images revealed details no diver could ever capture. The exact geometry of the chambers, the extent of the limestone formations, the precise structure of the vertical wall dropping from turquoise surface water to absolute darkness. The Blue Hole is part of the Belize Barrier Reef Reserve System, a UNESCO World Heritage Site since 1996. That formal protection recognizes that Lighthouse Reef Atoll and the hole it contains are part of the second largest barrier reef system in the world, the Mesoamerican Reef, which stretches for 1,000 kilometers along the coasts of Mexico, Belize, Guatemala, and Honduras. The reef surrounding the hole is among the healthiest in the Caribbean. Its proximity to open ocean brings large pelagic species, hammerhead sharks, bull sharks, rays, that don't appear in shallow coastal reefs. The hole, ironically poor in life on its inside, is a concentration point for predators that patrol its edge. Looking at the blue hole from above, whether from an aircraft or a NASA satellite image, is to visualize on a comprehensible scale what happens all across Yucatan just a few meters below the surface. A vast, dark, flooded underground world, separated from the surface only by the thickness of a rock that water patiently dissolves. The hole simply made visible what normally stays hidden. The transition between the world humans inhabit and the system of chambers and tunnels running underneath, recording in their limestone walls the climatic memory of 150,000 years of ice, thaw, formation, and flooding. The glittering surface of the Caribbean Sea reveals none of those stories. The hole in the reef does. More people have walked on the moon than have explored the deepest sections of some underwater cave systems. The Yucatan Peninsula has 6,000 mapped cenotes, more than 350 identified caves, and more than 1,600 kilometers of tunnels discovered since the 1980s. Most remain unexplored. The Ox-Belha system, with its 435 mapped kilometers, sustains its ecosystem on methane. The gas forms beneath the forest floor and migrates into the caves, where bacteria consume it and become food for crustaceans and fish. The underwater caves of Yucatan are at once the most preserved archaeological archive in the Americas, the largest cave ecosystem on the planet, a geological clock that records the last ice age on limestone walls, and a territory where 300-million-year-old remipedes swim in the dark, just a few meters below the tropical forest and the hotels of the Riviera Maya. 12 people walked on the moon. That number is precise, not poetic. 6 Apollo missions landed with 2 astronauts each between July 1969 and December 1972. The comparison to the Yucatan caves is not hyperbole. The most remote sections of the Ox-Belha, passages more than 10 kilometers from any entrance, requiring hours of travel with full technical gear, have been traversed by teams whose names would fit on a list just as short as the one for lunar travelers. Cave diving is one of the most restrictive forms of exploration that exists. It demands years of specialized training, redundant equipment designed to handle triple failures, and intimate knowledge of systems where a navigation error kilometers from the exit is irreversible. The methane discovered in the Ox-Belha overturned established assumptions about where the energy comes from to sustain ecosystems in lightless environments. The prior assumption was that organic matter from the surface, leaves, branches, dead organisms, fell through limestone fissures and served as the nutritional base for cave organisms. Research published in 2017 revealed that in the deeper reaches of the Ox-Belha, too far from the surface to receive organic debris in any meaningful quantity, sustenance comes from another source. Methane generated by the decomposition of vegetation under the floor of the tropical forest covering the limestone. Under normal conditions, that gas would rise and disperse into the atmosphere. Inside the aquifer, it gets trapped in the water and migrates downward, exactly the opposite of the expected behavior. Methanotrophic bacteria, which oxidize methane as an energy source, colonized this environment and became the first link in a food chain that requires no sunlight at any stage. Studies revealed that shrimp adapted to the Ox-Belha caves obtain approximately 21% of their nutrition through methane via these bacteria. This makes the Yucatan cave ecosystem structurally similar to cold seep ecosystems on the ocean floor, where methane or hydrogen sulfide replace sunlight as the primary energy source. But at a depth of just 10 to 20 meters, accessible to divers, rather than kilometers down in the ocean. The comparison to the ocean floor is more than a metaphor. The same evolutionary pressures that shaped organisms at deep hydrothermal vents, absence of light, food scarcity, chemically extreme environment, operate in the Anchialan caves of Yucatan, just at a completely different depth scale. Remipedes, eyeless fish, specialized blind shrimp, extremophile bacteria, all inhabit an environment that replicates, just meters below the surface of a tropical forest, the conditions normally found only in the inaccessible depths of the ocean. It is as if the deep ocean had been pushed upward and encapsulated inside the limestone, hidden beneath the forest. The underwater archaeology of Yucatan remains largely unexplored due to logistical constraints, not for lack of scientific interest. Every expedition requires teams of technically trained cave divers, underwater mapping equipment, documentation systems that function in darkness and under pressure, and safety protocols that consume substantial time and resources. A single exploration session in remote passages can involve hours of diving just to reach the area of interest. In those conditions, mapping 500 meters of uncharted territory is a significant achievement, a scale that completely inverts the intuition of anyone used to land-based exploration, where 500 meters is a 5-minute walk. The underwater archaeological sites of Yucatan have a characteristic with no parallel in land-based archaeology. The environment that would normally destroy them is exactly what preserves them. Moisture destroys wood, bone, and textile in tropical soils within decades. Underwater, in cold, stable, oxygen-poor water, those same materials persist for millennia. Charcoal from 12,000-year-old campfires retains its cellular structure intact enough to be precisely dated. Bones with recoverable DNA after 13,000 years submerged. Stone tools still with traces of red ochre adhering to the surface. No land-based archive in Yucatan holds records of those populations. The only archive that survived is underwater. The Riviera Maya, the coastal strip running from Cancun to Tulum, is one of the fastest-growing tourist regions in the world. Hotels, condominiums, highways, and theme parks continuously push further into limestone that is, on the inside, a network of flooded passages and preserved prehistoric campsites. Every new foundation drilled into the limestone is a potential intrusion into the cave system. Untreated sewage leaking from undersized septic systems dissolves through the porous limestone within days. Pesticides applied on nearby farms reach the caves without any chemical filtration. The most complete archive of prehistoric life in the Americas is being slowly compromised by the surface that no one can see from below. The exploration of the Yucatan caves has advanced enormously since the first systematic dives in the 80s, from isolated kilometers to hundreds, organized into systems whose maps look like neural networks seen from above. But the ratio of what has been seen to what still exists unseen remains lopsided. Every kilometer mapped reveals unexplored branches. Every chamber opened exposes corridors that disappear into darkness beyond the reach of the lights. The system has no visible end, only the boundaries of what has been possible to reach so far, with current technology, with available teams, within the safety limits that make the activity survivable. There is a symmetry that runs through every one of these cave stories. The same process that created them, water dissolving limestone, millennium after millennium, is the same one that preserved them, flooded them, stratified them into layers of fresh and salt water, sustained life in them for 300 million years, and ultimately hid underwater the campsites, the skeletons, the stalagmites, and the miners who existed before any civilization on the continent had a name. The Yucatan Peninsula looks solid from above: forest, reef, hotel, road. But it is thin limestone over an immense, wet void, where time moves more slowly than on the surface, where 300-million-year-old remipedes swim in the dark alongside stalactites that stopped growing 12,000 years ago, and where the next raindrop falling on the forest has already begun its invisible journey back to the sea, along the same path it has always traveled.